So without further ado, on your right screen, on my left, you have the content. And we'll try to work with both of these screens in some kind of logical order, although may not always be in the right page order. So we're going to go through and talk about categorical variable modeling in general very briefly, which is what we mentioned as a prerequisite for this course. Categorical variables being observed here, and that's only the first couple of pages where the variables are observed, and very soon the variables become unobserved, latent. But we're going to talk about modeling with categorical latent variables most of the day, give an overview of categorical latent variables, which we'll also refer to as mixtures, and often just talk about in terms of latent class models. We're going to talk about regression analysis, and that is with continuous outcomes, categorical outcomes, and with count outcomes. When I say outcome, that's the same as dependent variable. We're going to give examples of randomized trials with non-compliance, causal inference, and then turn our attention mostly to latent class analysis and give several examples and interspersing technical details about how to interpret your results and decide on which model fits best. And we're going to take the conventional latent class analysis further into what we will call confirmatory latent class analysis and latent class analysis where you add so-called random effects. And we will tell you about that in the next slide. And then finally coming to the most advanced type of modeling, combining continuous and categorical latent variables, and give examples of that. So this is just for those of you who are not familiar with Mplus, the philosophy, the reason we started this was that we felt that there were so many statistical methods that weren't used by non-statisticians. They weren't used by psychologists, psychiatrists, medical researchers. And partly because it's an inefficient dissemination of statistical methods that is occurring in the journals of biostatistics or psychometrics. It's a fragmented presentation. You read about these in technical journals, and there are many, many journals. We try to keep track of 20 journals or something that deal with methodology in different fields. And you get articles written that use very limited software, an R program that's written for that particular example of the article, and it's not very user-friendly for more general applications. So we felt that there was a need for an integration of the methods in one framework and in one computer program that's easy to use and at the same time very powerful. So you will find several unique analysis capabilities in this program. And this all started in 1998 in terms of the first release. That was preceded by several years of development with the help of National Institutes of Health, small business innovation research contracts and grants, where academics and business is supposed to merge, and Linda is business and I'm academic, so that worked fine. So that came out in November 98, and we had our first session, actually training session in Stockholm in the summer of 1998, so it's come a long way. The program didn't even have a name back then. February 2001 was version 2, and then now the latest version 5.2 happened in November 2008, although you should be using version 5.21, which was just released in, when was it? A few weeks ago. We have already forgotten. So version 5.21, the last one, just denoting the fact that there are some little glitches that are being cleaned up. It's a fairly small team, which means that we can work very efficiently. Apart from us, we have a full-time programmer at Thuy Nguyen, particularly involved with the front end of the program, and our statistical genius is Tiamer Asparohov, and then at taking care of business is Michelle Kahn and Gene Manninger. So it's a program that moves quickly forward. Right now we're moving on version 6, and to be released sometime we have stopped giving dates because we never know when we want to stop putting in new features. But there are already 3 or 4 very interesting features that will let everybody be surprised by, pleasantly surprised, we hope. That will probably come sometime in the fall. If you're more ambitious, maybe it'll come sometime early next year. So the general thinking is that you could put a lot of methods under one umbrella and find a unifying theme by considering latent variables. So there are many statistical concepts that are captured by latent variables, and on your right screen, many corresponding models that use latent variables. And we sorted into 2 columns, continuous latent variables and categorical latent variables. And in the continuous area, we've seen many models from the psychological factors that are hypothesized, measurement errors. In structural equation modeling, that's used quite a lot. But in general statistics, statisticians talk about random effects, which are continuous latent variables, capturing unobserved heterogeneity among individuals. And in survival analysis, you talk about frailties, unobserved qualities of individuals that make them differ in terms of susceptibility for death, even when you control for many variables such as age and gender. And liabilities is a genetically oriented term, which is also a continuous latent variable. And variables that vary on different levels in multi-level settings, giving rise to variance components on different levels, are also continuous latent variables. And when a continuous variable has missingness, it is latent. So missing data gets folded into this general context as well. And for categorical latent variables, latent classes, which is a way to sort individuals as opposed to sorting variables that you do by factor analysis. Cluster analysis has that feature. Finite mixtures is a term that statisticians use for categorical latent variables. And when you have categorical observed variables that are missing, well, then missing data falls into the latent variable setting. And on the right, you have the corresponding models then that I have alluded to, factor analysis, structural equation models, growth curve models, which we'll talk about tomorrow, Saturday, and also on Tuesday, which use the random effects on the left here, and the multi-level models, which is the topic of both Monday and Tuesday. But today, we'll talk about the rightmost column over there, categorical latent variables, and in the shape of latent class models. And the interesting thing is that Mplus, as it says here, not only puts one analysis on top of another analysis, all of the analyses are fully integrated. So you can combine pieces of different kinds of models into a new model that suits your application. And one way of summarizing this is to look at a model diagram, and we have a convention here that we'll use throughout these 4 days. You have boxes representing observed variables. X variables are the background variables, and sometimes we'll call them exogenous variables or covariates. And foreground variables are the dependent variables, Y. And if they are categorical or otherwise do not have variance-specific parameters, we call them U variables. And the latent variables are circles, F for factors, that is continuous latent variables, C for categorical latent variables. And you have all kinds of possible relationships here, and models specific special cases like the ellipse A talking about structural equation modeling, ellipse B talking about latent class modeling, and whereas we like to work in the whole box here. And you can also have multiple levels within cluster and between cluster, say student and school level analysis. So that's the convention, the notational convention that we'll use throughout here when we talk about generic examples and not talking about examples specific to an application. So in summary then, if you think through these boxes and combinations of concepts and models, you find that Mplus then is several programs in one. It's a very good exploratory factor analysis program by some recent developments led by Timur Asparoho, our statisticians on the Mplus team, I think we have a uniquely equipped exploratory factor analysis program with a rich set of rotations and standard errors for the rotated loadings. And it can be used together with all kinds of settings like multi-level exploratory factor analysis, mixture exploratory factor analysis, exploratory structural equation modeling. So you can have an exploratory factor analysis measurement model on top of a structural equation model. So that's quite interesting. It's a great structural equation modeling program. I think we have more features than other programs in that area too. It's a good item response theory program. It's a great latent class analysis program, latent transition analysis, survival analysis. We do both discrete time, event history analysis, and continuous time survival analysis, where there are some unique features involving latent variables. So you can do Cox regression with latent variables, for instance. Growth modeling, very well equipped for that, and multi-level analysis, very well equipped for that. And a special effort has gone into complex survey data analysis. So that was a grant from National Institutes of Health in the United States to develop all of these techniques to be able to handle national surveys where you have sampling weights, cluster sampling, stratification, and those kinds of features. It's also a very good program for methodological studies where you could do so-called Monte Carlo simulations, which we'll talk about here. So you can write whole dissertations based on this feature alone. And again, it's fully integrated in the general latent variable modeling framework. So you have all kinds of combinations between these features. So we just wanted to point that out and have it out there. So now, if you find these days of interest, but that things go by a little too quickly, well, then you're welcome to come to the United States. We won't handle the ticket, I think, but topic 1, here you see the 4 topics and 4 topics. You are dealing with screen number 2 here on the right. Those are the 4 days that we offer here. But really, the way we have it structured is we talk about factor analysis, structural equation modeling. It's going to happen in August at Johns Hopkins University, Baltimore. And topic 2 is the same topics, but for categorical and other non-normal outcomes, count outcomes, for instance. And then topic 3 and 4 are very important for what we'll talk about today, or tomorrow rather, and Tuesday. Talking about longitudinal analysis, growth modeling. That'll happen in March 2010. So every 6 months we go to Hopkins and give these courses. And we'll talk about survival analysis and all kinds of interesting missing data analysis, including non-ignorable missing data analysis. And here are the topics of this meeting here. Today, categorical latent variable modeling with cross-sectional data, and tomorrow, the longitudinal counterpart. And then, on Monday, multi-level modeling of cross-sectional data corresponding to all of the previous topics that have been talked about, adding a multi-level angle to that for cross-sectional data, and then the last day for longitudinal data. Now, having said that, I think even those of you who haven't had time to prepare for this, you will find that we'll give you a chance to jump in at topic 5 here, and we'll give you a chance to be able to follow it even so. So just a quick recap of categorical data analysis. What are the basic things that you need to know to be able to sink into this topic of categorical variables? And the reason we need to be able to understand that for observed variables is that we're going to use the same modeling ideas for the latent variables. And one very basic model idea is that of regression with a dichotomous dependent variable dichotomous or binary dependent variable. So we have a u variable, in the generic notation of Mplus, u is equal to 1 versus 0. And we're not going to model the value of u, but the probability that u happens. So we have the probability that u equals 1 as a function of, or given, or as a function of, say, 2x variables. And we're going to write that as a regression with the regression intercept beta sub 0 and the regression slope beta 1 times x1, beta 2 times x2. So this part inside of the bracket is a standard linear regression function, but we have a function f here where that linear part is an argument, but the whole right-hand side is actually very nonlinear. Think of an S-shaped curve, and actually we should have that on the other screen. So you have an S-shaped curve like this. This is what I mean by an S-shaped curve, and then that is what the f function orchestrates, in the sense that the y variable can only vary between 0 and 1, as probabilities should. You keep it within that range. So you have then the probability u equals 0 is just 1 minus the probability u equals 1. You only have two alternatives. They add up to probability 1. And f can be either a standard normal or a logistic function. And when we give it a standard normal function, it's a standard normal distribution function. And then we'll talk about probit regression. But when we have this logistic function, we're going to talk about logit or logistic regression. And phi, this is cap phi or cap phi, depending on where you were born. And that's the normal distribution function, which you have to look up in tables. The logistic function you can do on your hand calculator. And therefore, it tends to be more common, I guess. So take an example. You being getting lung cancer or not, and x1 being the dichotomous covariate of smoking or not smoking, and x2 being the continuous covariate of years spent in coal mine. And it can be described like this: as x2 increases, the number of years in the coal mine increases, the probability of acquiring a lung cancer goes up. But that is modified by the x1 variable, smoking or not. So you have two curves, one for x1 equals 0 and one for x1 equals 1. And you note then that for a given number of years spent in a coal mine, you have a higher probability of dying of lung cancer or having lung cancer if you are a smoker than if you are a non-smoker. And so this is an interesting feature that comes back again and again in different model settings, that when x1 is 0, the intercept is beta 0. When x1 is 1, the intercept is beta 0 plus beta 1. So it's two different intercepts, which shifts the curve sideways. But they have the same slope, beta 2, with respect to x2. So the same steepness of the curve, they're just shifted sideways. If you turn that into probits or logits, that is, you talk about the argument here only, then you have that corresponds to two parallel lines. So you can make two analogies here to remember this picture. One is ANCOVA. So you have a psychological experiment. You have you have treatment control, x1 equals 0, x1 equals 1. And x2 is some covariate, say a pretest, that you use to strengthen your analysis. And you say that you have equal slopes for treatment and control, but the treatment effect is beta 1, namely the slope for the treatment control dummy variable. And so the treatment effect is the distance between the curves here, or if you're doing the probability metric, distance here. So ANCOVA, this corresponds to an ANCOVA situation, one categorical x variable, one continuous x variable. Another example, totally different, comes from IRT, item response theory, and diff analysis, differential item functioning, where x1 and x1 would be, say, gender. male-female, and X2 would be your latent ability to solve a math problem. So then you're looking at, for two individuals with the same ability to solve a math problem, a woman, I better put women here, has a higher probability of solving that item correctly, and a man, of course, has a lower probability of solving it correctly. This distance would then be a differential item functioning, or in the older terms, item bias, something undesirable, something that you would want to understand why that happens. Because for a given answer, you would draw a different inference about the ability. So in that situation, you will see that in several other cases too. So it could be good to remember this example. Now, you can have different levels of ambition in trying to understand analysis of this kind, of the logistic regression kind. One is to just, as usual in linear regression with continuous y, continuous dependent variable, you can look at the sign and significance of the slopes, maybe not care much about the intercepts at all, but is that covariate significant in predicting the dependent variable, and what is it, plus or minus? Or you can add to the ambition level and talk about odds and odds ratios, which are natural quantities coming out of the logistic regression setting, or tying it back down to Earth, talking about the probabilities that the model implies. And on the right screen then, the formula laden sharp right screen, you have spelled out in utter detail how you go from odds to a logistic regression. So you start with the odds, and we have to then remember that odds is a ratio of probability that u equals 1 for a given x value versus, that is divided by, probability that it's 0. So the odds of lung cancer versus not lung cancer for a given number of years in a coal mine. And it turns out that the logistic regression model, the logistic function, which is 1 divided by 1 plus e to the power of minus, and then the logit, the intercept plus slope times x in parentheses. If you assume this model, this is the model that you assume, if you assume that, then the log of the odds, it turns out to be linear in x. If you look at the bottom right-hand corner, that's a final answer. The log of the odds is linear in x. So then so you interpret this as when x changes, well, you have that on the next page here, so I'll put it up. That gives you an easy interpretation. So we introduce the term of logit or log odds, which is what I call the argument of the function. And when x changes 1 unit, the logit changes beta 1 unit. So the dependent variable is the logit. You know, all of this is because we're so much more used to talking about and interpreting linear functions. So the dependent variable is linear in x. It's not e to the power of this thing on the right, but it is just this linear function. So the dependent variable is the logit or the log odds. So when x changes, beta 1 tells you how much the log odds changes, which means that if you take e to the power of beta 1, exponentiate the slope, then we're talking about how the odds changes, not the log odds. So that's made it popular to use logistic regression. And this is just high school and probably now grade 5 algebra to go through that you can do tonight, and I'll quiz you on that tomorrow. But you can follow this very easily. Now, if you haven't had time to study and are getting extremely curious about all these relationships, here are the books that we recommend, some of them at least. And Agresti has written 2 books, one the Fat Agresti book and the other the Agresti Light book, light one being Introduction, which deals with all kinds of general concepts of probability and probability models, including logistic regression. This book is focused on applied logistic regression only. A very good book is by Scott Long in the so-called White Sage series, as opposed to the Green series. Very good book that covers basic topics as well as quite advanced topics. So you may want to take a look at that. And we'll give you yet another book reference later on as we move on. So back to the idea of statistical concepts captured by latent variables. So far we talked about observed categorical variables on the dependent variable side. We won't be interested in categorical variables on the independent variable side. That is, if a covariate is dichotomous, that doesn't change our model. It changes our interpretation, but it doesn't change our model. The model type, linear regression versus, say, logistic nonlinear regression, is driven by the difference in the dependent variable type, not the independent variable type. So now we're going to switch to latent variables that are categorical and work in this area over here. So I'm going to try to cover some latent class models and some general finite mixture models. I don't think we have time to talk about, let's see, I'm over there. The discrete time survival models we won't have time for, and we won't have time for missing data models. But categorical latent variables really seem to be fitting very well with the substantive theories in many different subject matters, psychology, psychiatry, medicine, to just name a few. The intention is that we want to capture heterogeneity, and statisticians, they typically want to capture heterogeneity by random effects, continuous latent variables, but sometimes you need to distinguish between, you need to capture heterogeneity of a more qualitative kind. And that's when categorical latent variables come in. So we can think of categorical latent variables as corresponding to different unobserved subpopulations, latent classes or unobserved subpopulations. And you want to find out about these different subpopulations, if only to avoid biases in the estimation using regular models. We see that in cross-sectional data in medicine, psychiatry, and in market segmentation research, and in education. And we see it also in longitudinal data in medicine and in psychology and psychiatry. We're going to talk not only about latent class models, but also about regression analysis. We're always going to try to start with this standard regression model and then generalize it. So regression turning into latent class and going down then the trail towards longitudinal data. And we have a little delay here for some reason in the feed from back there. We'll let that sit and sort itself out and talk over here then. My page forward doesn't work for that screen. So on the left here then, you have a simple case of only one observed variable, y, only one observed variable y, continuous in this case. So it's on this axis here. And so it's a simpler case than regression analysis, actually. We have no covariate, right? We only have a dependent variable. And actually there are paper upon paper in the statistical literature on that case alone. You know, statisticians really like to dig into deeply into the special cases. Excuse me. So you have a continuous observed variable here, and you observe this distribution, the solid curve, but what you have underlying that are two different subpopulations. One subpopulation with a low mean, mu is a mean, and one subpopulation with a high mean. But you don't observe those distributions You just have a theory that they are the subpopulation that generate the data. And you want to know, first of all, you want to know how many underlying subpopulations are there, in this case 2. And then you want to determine the parameters, namely the mean for each, in this case. Maybe the variance is not that interesting. So you want to know how much higher is the mean for the class denoted C equals 1 versus the class denoted C equals 0. And we're going to try to have a very consistent model diagram scheme here. We're going to start with this model, which has one continuous latent variable, C, here. And it has 2 categories. So it's a binary or dichotomous variable with 2 categories, C equals 0, C equals 1, or 1 and 2. And we're going to have an arrow from C to Y. And in some cases, we are going to be able to draw on regression analysis to interpret what this arrow means. Think of this as having a dummy X variable, like gender, but it is unobserved. Let's forget that it's unobserved, but let's say that this is gender. What would this mean in a standard regression setting where you have only one dichotomous X variable? It means that the intercept of Y is different for males and females. That is, that the mean of Y is different for males and females, right? Dummy variable regression this way says that the mean of Y is different for the 2 categories of C, and by the fact that the intercepts are different. So we're going to draw on that analogy quite a lot. So this could be a hypothesis of a disease that is forming, say, prostate cancer that's forming in a man, and individuals we don't know who is on the pathway to prostate cancer, but it could be that if you study Y as the prostate-specific antigen in the blood, PSA, those who eventually will develop prostate cancer within the next few years have a higher PSA level than those who are not on the pathway to prostate cancer. And so the idea is you want to try to find out if one could consider having 2 subpopulations, a diseased population and a non-diseased population, and sort individuals into those classes. So a cluster analysis focus. This is with one dependent variable. Here we have 2 dependent variables, which is what we're going to focus on more today. 2 dependent variables, and it's drawn this way with a latent variable influencing both. So it has a factor analytic flavor. That is, the correlations between the 2 Y's is determined by them being influenced by the same C. So they correlate because they are connected via C. And in fact, it's the only way they correlate. There's no extra correlation between them directly, but everything goes through C. That thinking holds also for categorical latent variables, not only for continuous factors. So this is the latent class setting, and it is then, for continuous variables, latent class analysis is often called latent profile analysis. A couple of slides forward, you will see all the different abbreviations, acronyms for different kinds of models. So if you have, say, 3 classes here, the way it works is that you have Y2 and Y1 on the axis. Overall, they correlate. That is, the observed distribution is one where there's a positive correlation, a positive linear slope. But within each of the 3 classes, there is no correlation. No correlation in any of these 3 classes. But the fact that the classes are arranged as low, medium, high make them correlate overall. So this is a distinction that people often forget. They say, well, I don't want to assume 0 correlation between the variables because I believe my variables are correlated. Well, that doesn't contradict. The variables are correlated, but within each class, they are uncorrelated. By definition, the latent class or latent profile model defines itself by saying that the Y's are uncorrelated within class, the conditional independence assumption. And we're going to see towards the afternoon that we can relax that assumption, that specification, and work with more general models, factor mixture models. So then top right, we have a regression setting. y5 on the dependent side and x on the covariate side. And overall, we have a regression line positive here. But in this case, we see that that is due to having one latent class with a very steep slope, starting higher intercept, higher slope, and another class having a lower intercept and a lower slope. So a mixture of two classes. And that's represented by the picture on the right. If you look at y5, top right, and x, and c. Let's ignore the first four y's here for a second. So you have those three variables, y5, x, and c. And we're saying that x influences y5. And what do the arrows from c mean? Well, let's learn this once and for all here, because it's going to come back many times throughout these 4 days. C pointing to y5, we already said that that means that the intercept of y5 in y5's regression on x varies across the two classes. So the intercept varies across the classes is what that arrow says. So that is like we are regressing y5 on not only one variable x, but we're regressing y5 on two variables, the second variable being a dummy variable c. Let's just ignore that it's latent. It is a dummy variable c. Whether a variable is latent or not will become less important from a statistical modeling point of view. It'll be more important from an estimation point of view, maximum likelihood estimation using, say, the so-called EM algorithm. The EM algorithm. We'll talk about that a little bit. Now, this broken arrow, a broken arrow here, is not a regression line. It's not a regression arrow. It says that the slope of y5 regressed on x, that slope varies across the classes of C. So a high slope and a low slope. So a broken line is an assignment saying that most often used for slopes that vary across the classes. So we're going to see that come up in a lot of different, surprisingly many different contexts. And here, just for the fun of it, we added y1 through y4 in a latent class type of measurement model of C, because the psychometrician's knee-jerk reaction, whenever you have a latent variable, try to measure it. So you have then 4 measures of C, where C is a latent variable that influences how X influences y5. So it's a combination latent class regression model. Already we're putting things together. And finally then, a frequency of heavy drinking is an example of longitudinal data where you observe individuals from age 18 to 30 here. And this picture is supposed to represent two classes, two latent classes. One, the class is represented by the average developmental curve, the thick curve here. This is the normative curve with the more interest in the heavy frequency of drinking, or high frequency of heavy drinking in the early 20s, and a non-normative curve which drinks more and doesn't slow down as they approach a wiser age. Those are the thick lines, they are the averages, and then there's individual variation around those general themes. They are the thin lines. So the thin lines are the individuals. They can be individual variation. Not everyone who is on the normative path drinks as much as the average. Some are lower, some are higher, but they share the same general shape. The shape is this quadratic one. Same for the shapes of the non-normative class. And the way you can show that pictorially is as on the right. You have frequency of heavy drinking is your y variable repeated at t different time points. Same measure, same question given to these individuals as they grow older over time here. And back here is the latent class variable C, which has two categories. C has two classes. And here are three more latent variables, continuous latent variables, and they are continuous latent variables that are thought of as random effects. And they are the ones, it's three because you have an intercept, you have a linear slope, and you have a quadratic slope. Intercept, slope, quadratic slope. Those three continuous latent variables, random effects, are what gives rise to the individual variation around the means. So you have C deciding if you are in this shape or that shape, and then these I, S, and Q random effect growth factors deciding how much variation there is in the three growth factors that guide the development over time. So this topic we're going to talk about tomorrow quite a lot. But just to give you a feeling for how these things hang together. And they're all in this framework. And here you have a nomenclature for, I should do it this way. You have all these different kinds of models, model abbreviations used in the literature, LCA, latent class analysis, and we're going to talk about factor mixture analysis. We're going to talk about tomorrow latent transition analysis. So here they are structured by the outcome scale. Is it continuous or categorical? How many time points do we consider? How many of outcomes? How many measures per time point? And will we allow for within class variation or not? So we're not going to go through this now, but you have that list for completeness. And here are the some references that you might be interested in. Here's a very good book on latent class analysis, which starts fairly introductory and goes very advanced. Edited book, very good one. Lots of examples there, and we have worked through many of those examples using Mplus. Here's a very good book for those who are more statistically oriented, McLachlan and Peel, Finite Mixture Models, General Statistical Treatment. Here are two of my efforts to sort of write about general latent variable models. Here's the most recent one, overview of all kinds of different latent variable hybrid models. So with that, I think we can turn towards the first real topic, and I'll hand over to Linda.
Okay, so now we're going to talk about a couple of regression mixture examples. And the first one you see on your right screen, and this is an example that's taken from data analyzed by Fullman and Lambert. The reference is given at the bottom of the screen if you're interested in taking a look at that. And what they did was they looked at these blood parasites called trypanosomes, and they were interested in knowing what dosage of a type of poison they would have to give to these parasites in order to kill them. And so if you take a look at the diagram on the, well, let's take a look at the picture first. So the y-axis is the probability of death of these parasites, and the x-axis is the dose of the poison, the log dose actually, that is going to be used. And the broken line represents the data. So that's what the data looks like if you plot the probability versus the log dose. The line in the middle, the solid line, is a simple logistic regression, not taking into account that this might be a mixture of populations, but just a regression on the whole sample. And if you look at that, you can see that for certain parts of the data, we have an underestimation here at the beginning for the lower doses, and up here we have an overestimation if we use a simple linear or a simple logistic regression, not taking into account that there may be heterogeneity in the data. So what they did is they did a mixture model, which is shown, which we've depicted here. The U in the box represents an observed binary variable, so an observed binary dependent variable. The X is an observed covariate, which is the log dose of the poison, and the U is 0 or 1, either dead or alive, and we turn that into a probability when we're using logistic regression. That's a good way of depicting our results. C, as always, represents a categorical latent variable. And like Banks said, you can think of it just as a dummy variable, just a shift from one class or one value to another, one class to another in this situation. And when we have the solid line pointing at the dependent variable, what that means, as Banks showed earlier, is that we're going to allow the intercept in the regression of u on x to vary over classes. Now we don't have a broken line arrow pointing to the line that depicts the regression of u on x. So that means in this example, we're not going to estimate a model where the slope varies over classes, only the intercept. So just so you get used to the diagrams and what they mean. So here we're going to have a logistic regression of u on x where the intercept is going to be allowed to vary across classes. And if you take a look now at the picture again, at the scatter plot, you'll see that we have two curves now, the upper curve and a lower curve here. And those represent the results in the two classes. So you see here in the bottom, as the dose increases, the probability of death does not increase until you get to a fairly large dose, and then the probability of death increases. For this class of parasites, it's very difficult. You need a very high dose of the poison. Oh, it's getting dark. A high dose of the poison to actually kill the animal. Okay, and another way that we might use mixture regression is in a situation where we have the randomized response modeling of sensitive questions. Probably most of you are familiar with the fact that when you do a survey or when you do interviews of people and you ask them questions about drug use or other sensitive topics, people sometimes don't tell the truth. And that can be a problem for you when you're analyzing your data because you don't have true responses. But you could consider using this type of regression, mixture regression, to set up a study where you used dice and you allowed people to roll a pair of dice and see what their answers are privately with nobody else knowing. And if they roll 5 to 10, they would tell the truth about the question, did you take hard drugs in the last year? But if they rolled 2, 3, or 4, they would just say yes. They wouldn't answer whether yes is true or whether yes is false. They would say yes. And if they rolled an 11 or 12, they would just simply say no, whether no is the truth or not. So they would be in control of the dice, only they would know it, and so therefore they would be more likely to answer truthfully. And so then you would have two latent classes. Class 1 would be people who answered truthfully, and class 2, people giving the forced answers. And we know the class probabilities for classes 1 and 2. We know how many people are in class 1, and we know how many people are in class 2, because we know if you roll a pair of die, how many times you're going to get every combination. And so that is going to determine the class probabilities. So then we can have a model like on your right screen where we have U on X, and U can be, U is the drug question. Have you taken drugs in the last year? And X can be any kind of a covariate. And you see here we have the categorical latent variable C pointing to the dependent variable about drug use, saying that the intercept is going to vary, and the broken line saying that the slope is going to vary. Now, all we're interested in is class 1, the truthful class. So for class 1, we want to know U on X. We fix the class probabilities. For U on X, for the untruthful class, we just fix it 0. And everything else is fixed in the model except the regression of U on X for class 1, the truthful class. So in that way, the intercept and slope you estimate for class 1 are going to be the true answers. And you eliminate the untrue answers by using this randomized response model. So there's a second example that you might want to think of how you could use mixture regression. And the one thing about mixture modeling, and we're going to talk more about this as the day goes on, but when you do know something, when you know something about class membership, like in this example, you can use that to fix information and then end up estimating what you're really trying to get at. And I'll be showing an example of that after Bengt gives the next discussion. It's your turn.
I was having such a nice time with my coffee here.
Oops.
Okay, so now we've talked about binary dependent variables, and let's now talk about counts. That is, how many times something happens. So you may ask an individual, how many times in the last month did you use certain drugs, for instance? And with this light, I think we can look at either screen here. Why not this for a second? So just to remind you of basic modeling blocks for counts, for instance, Poisson regression. And Poisson is a way to describe the probability of an outcome. And it does so using this seemingly complex formula, but it's only e to the power of something, and there's a lambda. It's a lambda parameter. Lambda is the rate at which a rare event occurs. The distribution may look like this. So in the last 30 days, you use this drug 0 times, or many individuals use the drug 0 times, but then you have this rapidly declining histogram with a certain rate or a certain mean, in this case 0.5. And this means that you actually have a regression equation which is neither linear nor logit or probit, but in this case it's the log, the e-log or the natural log of lambda that is a linear equation. So the natural log of lambda is a linear equation. So again, trying to bring things down to the linear situation where the dependent variable changes to log rate. Now that's a popular distribution in statistics, but it's right away recognized that it doesn't fit the data very often because it tends to misestimate the number of people in the 0 bar. Because the Poisson variable has the requirement that the mean is equal to the variance. That's a peculiar requirement. Whereas the data often have variance that is bigger than the mean, due to the fact that we often have a preponderance of zeros. We have many zeros here, many more relative to the tail than the Poisson would predict. So here is where a latent class model comes in naturally again. To take into account that data have variance greater than the mean, we work with the so-called zip regression, zero inflated Poisson, and that is as follows. First of all, you try to describe pi. Pi is now not 3.14 but a probability. Probability of being in the 0 class where only u equals 0 is seen. Think of this as individuals who don't use drugs. Individuals who don't use drugs. So this is the probability of not using drugs at all, not being a drug user. And then the opposite class is the 1 minus pi, not being in the 0 class, that is being a drug user, and then having the number of times in the last month that you use drugs follow a Poisson distribution. And that's an interesting one. It's a mixture at 0. So the probability that you see 0 drug use in the last month is a mixture pi plus 1 minus pi times e to the minus lambda. First, let's think about this substantively without the formulas. So you observe you get a zero response from a person. This model recognizes that that zero response could be for two totally different reasons. It could be that the person is not a drug user, or it could be that the person is a drug user but did not use drugs in the last 30 days. So the first part corresponds to not being a drug user. Second, being a drug user but having U equals 0 for some reason. And U equals 0 is e to the power of minus lambda. If you put in U equals 0 up here and think about it for a while, you get e to the power of minus lambda. That's the Poisson part. So it's a mixture at 0. And we're going to see different kinds of mixtures, not at 0 only, later on. But first here, a mixture at 0, that's what the zip regression is. And, you know, the fact that you have two ways of getting people having U equals 0 means that you can better accommodate a high pile of people here relative to the tail than you would be able to do with the standard Poisson. So actually then the zip model implies two regressions, not only the log rate regression at the bottom, but also a regression for the logit of pi. And logit is, as we know, the log odds of pi. That is the odds, we're dealing with the odds of being in the non-using class, the non-drug using class. And this is a standard logistic regression equation with intercept gamma sub 0 and slope gamma sub 1. So you have one regression for determining if you're a drug user or not, and one regression determining how much you use. And they are different coefficients, could even be different covariates. So that's a powerful model. And however, it's not powerful enough for the statisticians to be satisfied, because they also have negbin, as they say, or the negative binomial regression. And you know, if you look at the bottom left here, the log rate in Poisson, like in logistic regression, does not have any residual term. It's sort of the conditional expectation part of the linear regression. There's no residual e here or epsilon. But you could add an epsilon, an unobserved heterogeneity, in terms of influencing the number of times you use drugs. Little epsilon here. And then you get a negbin type of thinking. And you avoid the Poisson assumption of equality. This is E and V here, are expectation and variance, the mean being equal to the variance that we talked about before, mean equal to the variance. But for the negative binomial, the mean is lambda and the variance is lambda plus lambda times something that involves a new parameter, alpha. So you have an alpha parameter, a heterogeneity parameter, or a dispersion parameter as it's called. Negative binomial with alpha 0 gives Poisson. When the dispersion parameter is alpha is greater than 0, we get a model that gives substantially higher probability for low counts and somewhat higher probability for high counts than Poisson. So very often people use the negative binomial instead of the zero inflated Poisson. So you don't need a zero inflated concoction, zero inflated creation of having a zero class if you use the negative binomial. So it's popular because of that. And there are many variations on that theme. You can have zero inflated negative binomial, which gives you an even higher possibility of capturing these people in the 0 point. And you can even have a zero truncated negative binomial. And that is a negative binomial where you can only observe positive counts. For instance, number of days stayed in the hospital. If you're already in the hospital, you're not going to have 0. You're going to have 1, 2, etc. And that's a so-called zero truncated negative binomial. And connecting with models we're going to talk about tomorrow, you also have hurdle models or two-part models. Two-part models, but I'll leave that for tomorrow. Now, you can even have mixture zip. What do I mean by mixture zip? We already said that zip was a mixture. It was a mixture at 0. But you can have a mixture above zero as well. You know, you can have people who are not drug users, people who are drug users but they don't use that much, people who are drug users and use very much. So you can have three classes where one class allows for a mixture of people who do use. So you have then a Logodds model for being a certain class, and then you have the log rate model has a class variable c. In this case, we let the intercept have a subscript c. We could have the slope as well. So the intercept is different for different users, a high intercept or a low intercept. And there are all kinds of generalizations of that for the negative binomial as well. Now, I'm not going to go through this all, and I'm not even sure I'm going to go through this example. We're going to let... well, this must be confusing for you, right? Here's an example that I think maybe we don't have time to go through.
Briefly. Briefly.
Yeah, let me just briefly give you an overview of this. This is an example from a book by, here I would pronounce it Hilbe, but I think it's Hilbe in the United States, Negative Binomial Regression. He talks, since we were in Europe, we thought of having a spicy example here of marital affairs. Counts of marital affairs in the last year. You have the count here. Count here up to 12 in the last year. Maybe it's a politician or something. And you have two models here. You have the Poisson model trying to fit this, or a negative binomial trying to fit this. And you see that if you look at the broken curve here, it's the same in the two. It's the observed data. A lot of people at 0, and then it goes down very rapidly. You have a little peak at 7 here. I don't know why 7 is... this is in the last year. That would be, bi-monthly. But in any case, so you regress that onto having kids, marital happiness, religiosity, and years married. So in the book, Hilbe, he goes through a lot of different models, but he focuses on the negative binomial. Now, I'm not going to go through this example because you can go home and watch this on your computer yourself, because we have so-called web talks, some of you might have seen. So there's a recorded web talk that you get to from our website that discusses this analysis that I describe on these pages, where I go through a whole set of models just to show you that that's possible in Mplus. I don't know how many models there are, but you have the Poisson first here. And what we keep track of is we use maximum likelihood estimation, which we'll talk about after the break. So we get a log likelihood, which we want to have high, and maximize the likelihood. And we record the number of parameters, and we have something called BIC. BIC stands for Bayesian Information Criterion. We're going to describe that. We want low values. I'm sorry, what?
Is that residual? Like a residual?
No, it's not a residual. It's a function of the likelihood and the number of parameters. So it balances the two. You want high likelihood for few parameters. So it's weighing these two together. We'll show you. So anyway, so Hilbe says the negative binomial is much better. Minus 724, its likelihood down here. Likelihood here is much better than the Poisson likelihood of minus 1300 down here. High is good. Even you have to work in the negative sign. So this is better than that, and this is better than that. BIC is much better for the negative binomial. And then you can add the zero inflation to the two, and the negative binomial is still better, still a lower value. I'm just giving you a quick rundown of this. But when you go to the 2 class, things start to get even out a little bit more. And when you get to the 2 class zero inflated Poisson, you see that zero inflated Poisson actually has a better or lower BIC than the 2 class zero inflated negative binomial. So for this example, Hilbe would not have needed the negative binomial, he could have just gone to a two-class zero-inflated Poisson. This is an example then of a mixture of two kinds. You have the group of people who don't have marital affairs, and then you have the group of people who have a few of them, and then a lot of them, okay? So that there are really three classes. When we say two-class, we mean a mixture of those who participate in the game. So zero-inflated is really one class in itself. So here it's a two-class means really three classes of people. Anyway, you may want to listen to that talk, and you will see all the possibilities, and maybe you want to get the Hilby book. But let me just finally say that here is the input, the Mplus input for that, which will just give you for your own reference. We will not go through it at this point, but it will become clear to you how to set it up once you hear the later examples. So,
should I do this? Start it now and then finish it after the break? Okay. One other thing I wanted to mention about these various count models that Bengt talked about, they came out in version 5.1 of the program, so they're not in the user's guide, but they're in the 5.1 addendum. There's an examples addendum and a language addendum on the website with the user's guide. So if you're interested in any of these models for count variables, that's where you'll find the documentation. So now I went through two mixture examples that had binary outcomes, and Bengt did one that has a count outcome, and now we're going to look at one with a continuous outcome. And in the context of randomized trials with non-compliance. And so this is a situation where you assign individuals to a treatment randomly, so randomly is the key, to treatment and control conditions. And you do this randomization because you want to be certain that the treatment is the cause of the difference you see in the dependent variable at the end of the treatment. And you know something about, so you have your treatment and your control groups here, and you know in the treatment group that some of the people complied and took the treatment, they actually showed up, they participated, and they took the treatment. But you also know that there are people in the treatment group that didn't take the treatment. So we call the ones who took the treatment compliers, and the ones who didn't take the treatment non-compliers. So we know something about the treatment group. We know who complied and who didn't. In the control group, we know that the control group and the treatment group are randomly equivalent. So we know in the control group there are also compliers and non-compliers, but we don't know who the compliers and non-compliers are in the control group. We also know that in general, compliers and non-compliers are not statistically equivalent, that they differ in various ways, maybe education, motivation to get better, whatever it might be. The people who comply to the treatment and those who don't, they're different, and they're different in the control group and in the treatment group. So there are four approaches that people take to estimating treatment effects, and one of them is just to take the treatment group, the full treatment group, those who complied and those who didn't comply, and compare them to the full control group, which is referred to as ITT, intent to treat. And that really isn't what you want, because what you want to know is the treatment compliers versus the control compliers. So your treatment effect is going to be watered down if you throw in the people who didn't comply to the treatment. A second approach is called per protocol, and they take the treatment compliers and they just compare them to the entire control group. And we know that's not quite what we want either, because we know that the control group has both compliers and non-compliers in it. So that's not the comparison of treatment compliers to control compliers. And then a third approach is they take the treatment compliers and then they throw in the treatment non-compliers in with the control group, and they make that comparison. So treatment compliers versus control plus treatment non-compliers. And they call that as treated. So these are in the literature what they refer to these as. And that's not what we want either. So to make a long story short, what we want is a mixture analysis. The complier average causal effect, or the case model, the reference is at the bottom here, Little and Yao. And what that does is it allows treatment compliers to be compared to control compliers, which is what we want, and treatment non-compliers to be compared to control non-compliers, which would have no relationship really. But so we can get at what we want by using this case model. And here's, well, actually, let me move this one too. So we have two examples in the user's guide, 7.24 and 7.23. And they both show two different ways of estimating this model. So if you look at the two screens, you'll see that the only difference between the right and the left screen is this observed variable u. So on the right screen, we use what's called training data to estimate the model. On the left screen, we use the u. It's a dummy variable, and for treatment compliers, get a 1. Treatment non-compliers get a 0. And all of the control group gets missing data, because we don't know for the control group who's a complier or who's a non-complier. And the basic idea is you regress y, a dependent variable continuous, here it could be categorical also, or count, on a treatment variable z, and you have two classes, one class compliers and one class non-compliers, and what you want is the intercept and the slope of the complier group. That will give you your true treatment effect, so your y on x. So that's the basic idea of this type of model. And we have an example, which probably we don't have time to go through totally, but let me instead talk about one part of it that might not be self-evident, and that's the training data. So in Mplus, we have the ability to use training data. And that's what I was saying before. When you know something, then you can use the training data to define what you know about the latent classes, and then the rest kind of falls into place from that. So we know in the treatment group who are the compliers and who are the non-compliers. And we know we're going to have two classes, one complier class and one non-complier class. So training data includes one variable for each latent class, and a person gets a value of either 0 or 1 for each of the variables. And 1 means that the person, a 1 indicates the individual can be in the class, and a 0 not. So at the bottom you can see our situation, we have two classes, compliers and non-compliers. We have 3 groups, control group, or 3 groups of people that we know stuff about. Control group, treatment group, compliers, treatment group, non-compliers. So for the control group, we give them a 1 for each of the variables, the training data variables, because they could be compliers or non-compliers. We don't know for sure, so they could be in either class. But for treatment group compliers, we know that they can only be in the complier class, so we give them a 1 there and a 0 for the second class. Treatment group non-compliers, likewise, can't be in the complier class, so they get a 0, and they get a 1 for the non-complier class. So this is the same as using the dummy variable approach, where the treatment group compliers get a 1, non-compliers a 0, and the control group missing. This is what the path diagram looks like for this. So our dependent variable is depression. It's a continuous variable. And we have a latent class variable with 2 classes, compliers and non-compliers. And you can see in this example, we regress the latent class, the categorical latent variable, on a set of covariates, age, education, etc., down to non-white, because we want to understand who are the compliers and the non-compliers. How do they differ from each other? And then we regress the dependent variable depression on a treatment variable, an earlier depression measure, and some type of a risk measure. So you can see we have different covariates for the dependent variable and then different covariates for the categorical latent variable. And this C on X here is a multinomial logistic regression. Since this is continuous, depression on these is a linear regression. And as I said earlier, for the complier class, the regression of depression on treatment gives us the treatment effect that we're interested in. And that should be where we end.
I just want to add some general comments on this set of models, just as an overview. So what we talked about this morning is one single dependent variable, and that doesn't carry that much information. I mean, it carries information about its univariate distribution and its relationship with covariates x's. But for those models, particularly when the dependent variable is not continuous but categorical or count, typically it's only the intercept that is allowed to vary across classes, not the slope. But you have now seen two examples where the slope also varies across classes, this being one of them, the non-compliance modeling. You know, the slope varies across these classes here. But those examples are successful because, despite having only one dependent variable, they are successful because you have a design. So the strength of having a design, this is a randomized trial, and we assume that the slope is 0 for non-compliers. There is no effect of treatment on the dependent variable for non-compliers. The slope is 0, as we see here. You see, you have the setup for your files here. But that is only because of our design of a randomized trial. Same thing for the sensitive questions where we threw these dice and had a randomized design. You were able to allow for different slopes in the different classes. Now we're going to turn then after the break to models with many dependent variables where it's easier to let many more parameters vary across the classes. So at that point, maybe we should start having our first question and answer session. So who wants to be the first questioner? Okay, so since we're videotaping this, we'll repeat the question.
Yes.
The question is about slide 50 here on the right, and it has to do with identification matters. Do we have to assume that the box of covariates on the left, age, etc., are unrelated to Y? Is that what you're saying? Unrelated to depression?
Yes.
Yeah, okay, so that's a good question. You have an advanced question, I would say.
That's why it took.
Yeah, so you have these covariates influencing C. Can they also influence depression directly? And the answer is yes, I think, in this case. The difficulty, and you will see several references to this. Actually, we can have a reference here at the end of the section. You have references where my former student Bull Zhou has written a series of papers more geared towards this way of portraying the modeling than the statistical treatment by Angry, Simbins, and Rubin and Len Yao more applied here. This is, well, let's put it this way, more Mplus oriented. And what Bull Zhou discussed was the possibility of letting the treatment effect, the slope, be non-zero for both compliers and non-compliers. And she found that there was a detrimental effect of being assigned to treatment if you decided not to comply. And in that case, where you try to estimate a non-zero slope in both classes, you cannot also have these direct effects, I think. But it's a more fragile model. But that was a much, I want to hear much more basic questions now, and don't be embarrassed. Who can ask the most
Simple.
embarrassing question? No, sorry. The most basic question. Yes, please. Right, okay, so the question here, we haven't quite gone down to the basic yet, but we'll get there. So here the Poisson regression has the log rate equation here, and the question was about the Poisson. This gentleman can understand what is log rate because lambda sits in the exponent here, but it also sits here without the exponent. And why don't we also have an equation related to the linear part? And that's a good question. And I would refer you to good books on the Poisson distribution for that. So let's not go through that now because it becomes too technical, if you don't mind. But that's a good question good motivated question for digging into Agressi's book and sitting and reading them. Didn't I get out of that one? Okay, new question. So the question was about the residual arrow here. It denotes a little residual epsilon, and so we estimate a variance there. And as Linda said, the U variables don't have their own variance parameters. That's why you didn't see this arrow before. That's a good question. This is the level we want. Down to earth. Down to earth, yes.
Another basic question. What about the assumptions before we can do this? What are the underlying assumptions, independence, etc.? We're going to discuss that later on.
Yeah, no, we can talk about that now. Yes. So generally speaking, do you want to talk about some assumptions? I'll talk about some.
Well, not particularly. I mean, they're the same basic assumptions as in...
You mean IID?
Right.
Okay, so the assumptions are usually the usual ones about independent observations at this point. Next week we'll have non-independent observations because of cluster sampling. In this case, we assume that conditional on these, we call all of these variables in the boxes back here X variables, conditional on those and conditional on class, we assume that this is normally distributed. In this continuous case, normal distribution for this, conditional on X and conditional on class. Of course, the marginal distribution for Y, the distribution for Y is going to be very non-normal for two reasons. One, we have a mixture, and two, the X variables can be non-normal. There's still a fairly flexible model. Those are the basic assumptions here, I think.
So similar to logistic regression, the same type of assumption.
Yeah, I would say so, yeah. Except with the logistic regression, you don't have the conditional normality because you don't have a continuous deepener. Yeah, right. So linear regression, yes. More questions? Okay, so the question is about intercepts and means, and I think that's a very good question to bring up here. To just repeat, because it's coming back again and again, and so many people ask this kind of question that it's worth saying. So if you don't mind, I talk about it in the logistic case, but if you don't like the logistic, the nonlinear shape here, just focus on this part in here. So the dependent variable is a function of all of this. In this case, the loaded is this. And we said that the intercept is beta 0, but for the group that didn't smoke, x1 equals 0, the intercept is beta 0, and for those who do smoke, it's beta 0 plus beta 1. So you have two kinds of intercepts that correspond to these two curves. Now the mean, if you had a continuous variable that was a function of this, the mean is equal to the intercept plus the slopes times the means of the covariance. So the mean of the dependent variable is a function of the intercept and the slopes times the means of these variables. So it's not only, so with models that have covariance, Mplus estimates beta 0, beta 1, beta 2. It does not estimate the mean of the dependent variable. But the mean then becomes a function of these quantities. And that can become confused in growth models that we talk about tomorrow. So it's good that you bring it up. Okay, more questions? So then let's take a 20-minute coffee break and see you here at 10:30 again.